Consider a particle P revolving along the circle of radius A with the center of the circle at the origin O of the coordinate axes. This particle is called the reference particle. Let the particle revolve with a time period t and a constant angular velocity omega. This circle is called the reference circle. Since angular velocity is constant, we can say that the particle executes uniform circular motion. After the particle has moved for some time in the reference circle, take a projection of the particle on the y-axis. Label it as P'. As particle P revolves along the circular path, its projection moves up and down along the y-axis, with the mean position as O, and the extreme ends of this diameter of the reference circle along the y-axis as the extreme positions. Now, consider the position of particle P at time t equal to 0 on the x-axis. At the end of t seconds, its position changes. The angular displacement of the particle at the end of t seconds is omega t. At any time, OP denotes the position vector of the particle P. Consider the position of the projection of the particle along the y-axis when the particle moves through an angle omega t in a time interval t. The projection of the particle moves from the origin to the position as shown in the time t seconds. The displacement of the projection of the particle y is then obtained using trigonometric ratios of the right-angled triangle thus formed. Sine of the angle omega t is the ratio of opposite sides, which is the displacement of the projection of particle P', that is, OP', represented as y, to the position vector of the particle OP, whose magnitude is equivalent to the radius A of the reference circle. Thus, we get y is equal to A sine omega t. The motion of the projection is oscillatory, and its displacement varies sinusoidally with time. Thus, the motion of P' is simple harmonic motion. If the reference particle P executes uniform circular motion, its projection executes simple harmonic motion along the diameter of the reference circle. Here, A is the amplitude of the point P' executing simple harmonic motion. In another case, consider the position of the particle P at time t equal to 0, such that OP makes an angle phi with the x-axis. It then executes uniform circular motion with angular velocity omega along the circumference of the reference circle. At the end of t seconds, the position of the particle is such that OP makes an angle omega t plus phi with the x-axis. Then, the displacement of the projection of P executing simple harmonic motion along the diameter of the y-axis can be written as y is equal to A sine omega t plus phi, where A denotes the amplitude of simple harmonic motion, which is the radius of the reference circle. As with the projection of the reference particle on the y-axis, The point marked in green is the projection of the reference particle on the x-axis. As the particle revolves along the circular path, its projection moves to and fro along the x-axis, executing simple harmonic motion with mean position as O, and the extreme ends of this diameter along the x-axis as the extreme positions for simple harmonic motion. At time t is equal to 0, the revolving particle makes an angle phi with the x-axis. From this position, when it moves through an angle omega t in a timed interval t, its projection moves from s to t along the x-axis. The displacement of the projection executing simple harmonic motion along the diameter along the x-axis can be written as x is equal to a cos omega t plus phi, where a denotes the amplitude of simple harmonic motion, which is the radius of the reference circle. If the revolving particle began its journey from the end of the diameter, then the projection on the diameters along the y-axis, its displacement will be 0, and the initial phase angle phi would be 0. Then, displacement y is equal to a sin omega t, which is equal to 0. As you know, when a reference particle revolves along the reference circle with a constant angular velocity, omega, the projection of the particle on the diameters along the x-axis and y-axis executes simple harmonic motion. The particle executes circular motion with a constant velocity v, whose magnitude is equal to a omega, where a is the radius of the reference circle. For simplicity, if we assume the initial phase phi is equal to 0, then the two components of velocity v are v cos theta and v sin theta respectively in the directions shown. Then, the component v sin theta represents the velocity of the projection, which is executing simple harmonic motion on the diameter along the x-axis. Velocity of a particle in simple harmonic motion is equal to minus v sin theta. The negative sign is due to the direction of the velocity at that instant, which is opposite to that of the positive x-axis. If the particle has an initial phase phi, the velocity of simple harmonic motion can be written as minus v sin omega t plus phi or minus a omega sin omega t plus phi. Now, let us discuss acceleration in simple harmonic motion. Acceleration of the revolving particle will be the centripetal acceleration AC, denoted by v square by a or a omega square. The centripetal acceleration has two components: AC cos theta along the x-axis and AC sin theta along the y-axis. If the initial phase phi is equal to 0, the acceleration of the projection which is executing simple harmonic motion along the diameter along the x-axis, is equal to minus AC cos theta, since this component is directed opposite to the positive x-axis. If the initial phase phi is not equal to 0, the acceleration of the projection in simple harmonic motion is equal to minus AC cos omega t plus phi, which in turn can be written as minus A omega square cos omega t plus phi. On rearranging, we get minus omega square into A cos omega t plus phi. The quantity A cos omega t plus phi is the displacement x of the particle executing simple harmonic motion. Hence, the acceleration of the particle executing simple harmonic motion can be written in terms of its displacement as minus omega square x. Observe the graphs for the particle in simple harmonic motion. The first graph is displacement versus time for the particle in simple harmonic motion. The second graph is velocity versus time for the particle in simple harmonic motion. The third graph is for acceleration versus time for the particle in simple harmonic motion. From the graphs, we see that the phase difference between displacement and velocity is pi by 2 radian. The phase difference between displacement and acceleration is pi radian.